The scalar product, or sometimes referred to as the dot product, A dot B, is equal to the modulus of A times the modulus of B times the cos of the angle theta between them. So looking at this diagram, just to be clear, we've got the two vectors A and B. Notice both vectors must be directed away from the intersection point, and then that's the angle that we're talking about here. Now, if those vectors are perpendicular, that would mean that theta would be 90 degrees, and therefore cos of 90 degrees is 0, and so the dot product when you've got perpendicular vectors will be 0. If the vectors are parallel, then theta will equal 0, and cos of 0 is 1, and so the dot product, or the scalar product, will be the modulus of A times the modulus of B. So remember, these modulus signs in this context just means that we need to find the magnitude, which we do using Pythagoras' theorem. Now, there is an alternate form that we might want to use of the scalar product using unit vector form. So if A is this vector here and B is this one, then the dot product will be A1 times B1 plus A2 B2 plus A3 B3. Now just be clear, the answer to a scalar product is scalar, it's not a vector. Now what we're going to do next is we're going to prove where this scalar product in unit vector form formula comes from. So I've written it slightly differently using the unit vector terms. So we've got A1i plus A2j plus A3k dot product with B1i plus B2j plus B3k. So you can treat this like you would multiplying out normal brackets. So let's see what we would get. So we get A1i dot B1i plus A1i dot B2j plus A1i dot B3k. And then we'd have A2j times B1i plus A2j dot B2j plus A2 j dot B3k. We've got A3k dot B1i plus A3k dot B2j plus A3k dot B3k. So that looks rather unwieldy, doesn't it? So what we're going to use is some of the information that I've just given you. So I is the x direction, remember. J is the y direction and k is the z direction. And they are all perpendicular to each other. And therefore I dot j is nothing. J dot k is nothing. And k dot j is nothing, and so on. Okay, so that means we can eliminate an awful lot of this formula. Instead of crossing out the bits we're going to get rid of, I'm just going to underline the bits that we don't get rid of. So we'll still have this one, and this one. When the lines are parallel, so I would be parallel with I, remember we just get the magnitude. And so A1i dot B1i will actually just be A1 B1. And then A2j dot B2j will be A2 B2. and A3k dot B3k will just be A3 B3. So for our first example, we're being asked to find a vector that is perpendicular to 2i minus 3j minus k. So what do we know about vectors that are perpendicular? We know that the scalar product equals 0. So what we're just going to do is invent, if you like, this vector that we're trying to find. So I'm going to call it A, B, C. And what we know is that if we do the dot product with what we've got there, which is 2 minus 3 minus 1, that needs to equal 0. So that gives us a little formula here. So we've got 2a minus 3b minus c needs to equal 0. So literally what you're going to do is pick A and B to suit yourself and then work out what the C would need to be to make this equation work. So let's pick A equals 1, B equals 2, make life easy. So 2a will be 2, minus 3b will be minus 6, minus c equals 0, and so c would equal 2 minus 6, which is minus 4. And so one possible vector that is perpendicular to 2i minus 3j minus k would be 1, 2, minus 4. Writing it in unit vector terms, that would be I plus 2j minus 4k. In this question, we're being asked to prove that lines R1 and R2 are parallel. So remember, what do we know about parallel lines? We know that they're running in the same direction. And so what we're interested in is comparing the vector parts here. And what you'll notice is that this one over here is actually just a larger version of this one over here. So 4 minus 2, 6 is the same as, if we factorise out 2, as 2 minus 1, 3. And so because this one is just a slightly larger version of this one, that proves that they are parallel. It's quite common for you to be asked to find the angle between two vectors. We do this by rearranging the scalar product formula into cos theta equals a dot b over the modulus of a times the modulus of b. If you're given two vector equations of lines, just use the b parts for a and b. If you're given one equation and 2 points, first find the vector between those 2 points. So in this example, we're being asked to find the angle between the line R, as you can see here, and the points C and D. So as I said, if you've got 2 points, the first thing we've got to do is find the vector between the 2 points. So we want to find CD. So we do that by having D minus C, like so. That's going to give us minus 1, minus 3, 5. Okay, so we're going to call that one A in our formula, and our B in our formula will be the 2, 4 and the minus 2 from up here. So we need to find the dot product of these two. So we've got minus 1, minus 3, 5, dot 2, 4, 2. So that's going to give us minus 2, minus 12, plus 10, and all of that. So that's minus 14, plus 10. So that's going to be minus 4. So now we need to find the magnitude of A and B. So the magnitude, first of all, of A is going to be the square root of 1 squared plus 3 squared plus 5 squared, which is the square root of 1 plus 9 plus 25, so that's the square root of 35. And then the modulus of B is going to be the square root of 2 squared plus 4 squared plus 2 squared. So that's going to be 4 plus 16, which is 20, plus another 4, so that's 24. So let's put that all together in our formula. So that's going to give us cos theta equals minus 4 over root 35 times by root 24. And so we're going to put that into the calculator to work out what theta is. And to one decimal place, that gives us 97.9 degrees. Now sometimes they specify that what they want is the acute angle. This is obviously not acute, so if they need the acute version of that, then all you've got to do is take that away from 180, and so that will give us 82.1 degrees. So one more type of question here. Here they're asking us to find the shortest distance between the point A and this line. Now the shortest distance between a point and a line will be the perpendicular distance. So just think about it. Here's your line, here's your point A. Now the shortest distance is going to be this distance here, which will be the one that's perpendicular to this line. What we're going to do is use a bit of trig, but first of all we're going to need to find some parts. So the first thing we need to find is where x crosses this line. Now it can cross in lots of different places, so we're literally going to choose. So the way that we're going to choose is by just picking a value of lambda, and if you're smart you'll just choose lambda to be 1. So that would make this point x equal to 302 plus 1 minus 1, 2, which is going to give us 4 minus 1, 4. So that is going to be our point where it crosses that line. So what we need to do is find theta. We need to find that angle between these two lines. So we've got the equation of the line itself, and we've got this point x. So we're going to do what we've just been doing before. So we need to find first of all the vector ax. So that's going to be x minus a, which is going to give us 4 minus 5 is minus 1, minus 1 minus 2 is minus 3, 4 minus 3 is 1. And then we're going to use that formula that we had before. So we need to find the dot product of ax and r. So that's going to be the minus 1 minus 3, 1 that we have just found, times by 1 minus 1, 2. So that's going to give us minus 1 plus 3 plus 2. So that's going to give us 4. We also need the magnitude of these. So the magnitude of r is going to be the square root of 1 squared plus 1 squared plus 2 squared. So that's going to be the square root of 6. And the modulus of ax there is going to be the square root of 1 squared plus 3 squared plus 1 squared. So that's going to be the square root of 11. So let's put that all into the formula. So we'll get cos theta equals the dot product, which was 4 over root 6 times root 11. So let's find out what theta is. And if you put that into the calculator, what you'll find is that you get 60.5 degrees to the nearest tenth of a degree. So now what we need to do, we've got angle theta. We know how long AX is. So now what we're trying to find is this shortest distance, which is this distance here. So that is opposite the angle. So we're going to use a bit of SOHCAHTOA. So sine theta would equal the length we're after over the hypotenuse, which is AX. And so the length we're looking for is going to be equal to the hypotenuse AX, which was root 11, times by sine of 60.5 degrees. And putting that into the calculator, you get 2.89 to 3 significant figures.